Dear committee, my name is George Kuyumzoglou, and I am a PhD holder, a professor in Seneca and Centennial Colleges. I've been teaching since 2006, and I have a contribution to research in computer science. The topic of this presentation is computer graphics, and more specifically, illumination models, intro to illumination models, and the Phong illumination model. So let's get started with the presentation. We're going to start with an intro to illumination models. In the real world, lighting describes the interaction of light sources with surfaces and materials in the real world, of course. This means that every surface will emit, absorb, reflect, and scatter light. The final intensity and the color of each point of each surface, it's the summary of all the light paths reaching that point. That's how the real world works. In computer graphics, we use illumination model to that end. Illumination model in or lighting model in computer science tries to approximate typically the physics of light. To that end, we use an illumination model to simulate or approximate how light interacts with surfaces. And these models are also, of course, mathematically described using rendering equations. Rendering equation mathematically models all incoming light contributed to the color of a surface point or a surface. To that end, we use simplifications such as the simplification of light sources, simplification of materials, simplification of computation, and speed up techniques. Let's talk now about one of the most prominent, basically the most prominent illumination model, the Phong illumination model. The Phong illumination model was introduced in 1973 by Phong, and it combines three different components in order to approximate the real light conditions in a computer graphics scene. These are the ambient reflection, diffuse reflection, and specular reflection. If we want to see it like described mathematically, we say that the summary of ambient, diffuse, and spectral light create the Phong intensity or total intensity in a specific point. So let's get started with the ambient reflection, the first one. This is the ambient reflection or ambient light is the light that represents this. It's represented in the scene everywhere in the scene, and it's constant. Its mathematical equation is the ambient reflection coefficient times the ambient light intensity in that scene. We use the coefficient in order to control the brightness of this or the value of ambient reflection. We can see ambient reflection is in a teapot, visual object, which is like constant and covers the entire object. The second type, the second component of the Phong illumination model is the diffuse reflection. The diffuse reflection represents the light that hits the surface and scatters in many directions. We're not talking always about diffuse reflectors, like perfect diffuse reflectors that are pretty rare, but the light that interacts with the surface and scatters in different directions. Mathematically, it is described as the product of diffuse reflection coefficient times the light source intensity times the surface normal, and of course the maximum of zero or the dot product of the normal surface, the surface normal, and the vector point of the light source. So this means that diffuse reflection is greatly influenced by the position of a point or the surface of an object, and of course the position of the light source. We can see the addition of diffuse reflection on the same surface if we combine ambient and diffuse light. The last component is the specular reflection. The specular highlights are mirror-like reflection on the surface of an object. We can see them like in a bright morning. We can see like many specular reflections reflecting on every shiny object around us. And if we can see directly an example, ambient, diffuse plus specular creates this light reflection on the surface of objects. Of course, as we know practically, these reflections are associated by, are influenced by the position of the light and, of course, our point of view, because when we move our heads, we can clearly see that this reflection moves towards us or in any other direction. So its mathematical expression is calculated by the product of the specular reflection coefficient, of course, intensity of the light source, and the maximum of zero, or the dot product of the reflection of the light vector, which can be calculated and will be covered later in another class, and the view direction, right? So it's the reflection of the light source on the surface, or the ray of light on the surface of the object, and of course our view direction, which changes the position of the specular reflection. All that is and the power of n, which is the signness factor, which means which as it grows higher, it means smaller and sharper highlights. We can clearly see how it's the different components create the final result, like ambient plus diffuse plus specular highlights. If they combine, create a perfect small reflection. Summarizing, we talked about illumination models, describe light, that describe light, how light interacts with the surfaces and computer graphics, and of course, more specifically about the Fonck illumination model, which is expressed by the combination of ambient, diffuse, and specular highlights in order to create the total Fonck intensity. In the next class, we're gonna talk about the blink Fonck and shading. Thank you for attending the class. If you have any questions, please go ahead.